I will share my previous slides now. So this will be a continuation of what we have discussed last week. And there are 3 remaining topics here. All this one was shared already in Canva. Same thing with the sample problems that are hyperlinked to this slide. Okay, let me just go back to where I'm supposed to start. So here we are. We're now on the topic of heat exchangers. Guys, just give me a few minutes. Okay, so we are now on heat exchangers. I'm just going to discuss a few of the fundamental principles on the type of each of the heat exchangers before I discuss the necessary formulas that you will be using in tackling problems concerning heat exchanger design. Now, the simplest of all these heat exchanger is the double pipe heat exchanger. So this consists of a 2 concentric pipes. So you have one pipe nested inside another, and this is the cheapest and has the simplest of all design. So in the case of the double pipe heat exchanger, you can have several units that can be connected in series, so that in terms of capacity, it will be increased, or in terms of the total volume of material that can be processed, it will be increased. So you can have this connected in series. Now, in terms of how this particular heat exchanger operates, so that's how it operates. So it can either be in countercurrent manner or co-current manner. So countercurrent, meaning the heating fluid or the cooling medium is facing the feed to be cooled or heated. So flowing a countercurrent to the feed that is to be cooled or heated. If it's co-current, they enter the same side of the heat exchanger. Same thing with the side where they're living, the said heat exchanger. Now, in some textbooks, this is how your major reference books, this is how a double pipe heat exchanger is illustrated, primarily because they intend to show the shell side fluid and the tube side fluid in the illustration. So you could see here that the shell side fluid is of course the fluid that is passing through or flowing through the shell, and it is used as the heating or cooling medium. Now, the tube side fluid is oftentimes the one that is heated or being cooled. Okay? Then 47 hard time coming in. Now, another type is the shell and tube heat exchanger. So when we speak of a shell and tube heat exchanger, this consists of a bundle of tubes enclosed in a cylindrical shell. So the ends of the tubes are fitted into tube sheets which separate the shell side and the tube side fluids. Now baffles here are provided in the shell to direct the fluid flow, at the same time support the bundle of tubes. And this is how a shell and tube heat exchanger operates. So the one in red, the fluid in red is the hot fluid, and the one that is in blue is the cold fluid, depending on whatever is the objective of the said heat exchanger, whether it's for cooling or for heating. Okay, so you have a bundle of tube inside a shell. So that is why it's called a shell and tube heat exchanger. Now, this particular shell and tube heat exchanger can have several configurations. So in your handbook, you can even have the 3-6 configuration, 6 tubes in 3 shells. Now, what I have here are just the common ones. So you have a 1 shell, 1 tube bundle type of orientation. So you have the tubes inside the single shell. And the most simple the manner of presenting this particular orientation of the shell and tube heat exchanger is this one. So you have the tube in blue, and the one in red is your shell side fluid. So one tube bundle, and you have this shell side fluid in red. Now the 1-2 shell and tube heat exchanger is this one. So you have two tubes. So after your fluid passes through this region here, that's a single pass, it passes again to this region. So it's comparable to saying that you have one shell and two tube passes inside the shell. So you have one only shell housing, but your fluid that is being processed inside the tube bundles is being heated or cooled twice, because it has to go to this pass here, single pass, and this is the second pass. So it has two tube passes. As such, it's referred to as the 1-2 shell and tube heat exchanger orientation. Again, the blue are your tube bundles. So you have two tube bundles in here, two tube passes, and you have the red as the shell side fluid. So one shell only. Another one, another configuration is this 2 shell 4 tube heat exchanger, shell and tube heat exchanger. So you have this time 2 shells. So this is your this is your first shell, and this is your second shell. And in these shells, in each of these shells, you have 2 tube passes. So one tube pass in here, another tube pass in here. So it's likened to 2 tubes inside one shell. Then it goes further in here, processed in the second shell for the third pass, and then for the fourth pass before it leaves your heat exchanger. Okay, again, this is the orientation. You have 4 tube passes in 2 shells. As such, 4-6 shell and tube heat exchanger. That way you will be familiar with the different representation of the shell and tube heat exchanger. Now let's go to the plate and frame heat exchanger. So you have in this case a gasketed plate heat exchanger consisting of a stack of closely spaced thin plates clamped together in a frame. So plates that are clamped together in a frame. So a thin gasket seals the plates around their edges, and your plates can either be alloys, including stainless steel, aluminum, and titanium. Now this is how if it's open for maintenance, this is how your plate and frame heat exchanger look like. So it has several frames on it, and inside along or in between the frames is where your fluid is being heated or cooled. Cooled rather, depending on the purpose of the given plate and frame heat exchanger. Now, next is actually comparable to the plate and frame heat exchanger is the plate fin heat exchanger. So this consists essentially of plates. So we still have the plates, but these plates now this time are separated by corrugated sheets, which forms the fins. Now they are made up in a block and are often referred to as the matrix exchanger. So plate fin heat exchangers are referred also to as or called matrix exchangers. They are usually constructed of aluminum and joined and sealed by bracing. And this is how a plate fin heat exchanger look like. You have plates, and in between plates, you have the fins. Now, the manner of the orientation here of the flow of your fluids in this case is cross flow. Okay, and in here you have counter current flow. Now, the two configuration of how the fluids interact with each other. Although there is no direct contact, but that's the orientation of how they flow in the system. Now we go to the spiral heat exchanger. So a spiral heat exchanger can be considered as a plate heat exchanger in which the plates are formed into spirals. So it's just like comparable, let's say, to several pieces of paper. Let's say that's your plates, and then you roll those pieces of paper, so you have now a spiral. Okay, the fluids flow through the channels that is formed between the plates that have been rolled. So that's your spiral heat exchanger. And this is how it looks like. And this is its cross-section. Again, the blue fluids are the cold fluid and the red are the hot fluids. Now, another thing, a modification of the double pipe heat exchanger is the scrape surface exchanger, which is commonly used in the food manufacturing industry. Here, heat transfer to and from viscous fluids, especially food products and other heat-sensitive liquids, is often accomplished in scrape surface exchangers. Now, typically, they are double pipe exchangers with a fairly large central tube. So there is a central tube the diameter ranges from 100 to 300 mm, and it is jacketed. So it's having steam for heating medium, or it can have the regular water for the cooling medium. This is our scrape surface heat exchanger. So this is the scraper and this is the central tube. This is where the material that needs to be heated is processed, either heated or cooled down. And this is the cross-section of your scrape surface heat exchanger. So the service fluid, or the fluid that is either to transfer heat or absorb the heat coming from in here, is on the jacket. This is oftentimes jacketed. Now, so those are the common types of heat exchangers available in the industry. Now we go to the design equations, formulas that you will encounter and you will be using for, of course, heat exchanger related problems. Now in here, this is just a review on the lube mean temperature difference correction factor. Now, for countercurrent and co-current flow, the lube mean temperature difference is given by this formula. Now, I'll show to you in the next slide what is delta T2 and what is delta T1. So you have two differences in temperatures in the numerator, and in the denominator, you take the ln of these two temperature differences. So that would be the lube mean temperature difference. However, in the actual design, we're just using it, but we need to consider the temperature correction factor, and that's represented by F sub T, and it's to be multiplied to this one for your lube mean temperature difference. That way we get the delta T mean. It is the delta T mean that we are using when we determine the amount of heat that is being transferred. So you have noticed here in the formula that you have Q sub I, meaning we're basing it on the inside surface area, and it's equated to U sub I, A sub I, and delta T mean. This should be the same as this, or this should have the same value as the product of U sub O, A sub O, and delta T M, or that would be the delta mean, or the mean temperature difference. So you have the subscript O for outer and subscript I for the inner area. Now, this particular formula can also be compared to this one. This is actually the main area, shall I say the generic area that we can use based on the fundamental of heat transfer as I think introduced to you in your thermodynamics. So UA delta T. Now this UA delta T can also be equated to the delta T over the summation of the resistances. Okay, what is this resistances? So these resistances would actually account for the heat transfer coefficient, H sub I, inner, meaning based on the inside transfer area or the inner area, and then you have the H sub O here, the outer area, and you have the resistance due to the wall itself that separates the two fluids. So this is your R in here. This R is equal to 1 over the product of U and A, either based on the inside surface area, or it could be 1 over the product of U and A based on the outside area. You have here O outside and I as inside. Now, these are alternative formulas or equations that you can use based on the available information that is provided in the problem. So you use this formula in determining the Q. I'm referring to this one if you are provided with the overall heat transfer coefficient U, okay, and the area, the corresponding area for that, and you have the delta T. So you use this one. If it's not given, and in lieu of that, you are given heat transfer coefficients based on the inside and the outside fluids. So these are, by the way, heat transfer coefficients of the inner and the outer fluids. Then use this particular formula and use delta T over R for the Q. Determine the R first and then plug it in the formula in here and solve for the Q using this formula. That is if you are given heat transfer coefficients and areas. But if you are given overall heat transfer coefficients, you use this one. Okay? But oftentimes, class, what we use is this. The UA delta T mean formula, wherein we take into consideration the temperature correction factor. Now, but before we go to the temperature correction factor, let's have first the delta T log mean. How do we solve for the delta T log mean? It's based on the manner in which your hot and cold fluid transfers energy or in its flow orientation. Now, in the co-current flow orientation, so in one side of your heat exchanger, your hot fluid and your cold fluid are entering. So if they are entering your heat exchanger in one particular section, or they both enter in one side of your heat exchanger and leave also on the other side. So that's co-current. Of course, it's opposite the counter current. So what we have in here on the left side are the manner in which we draw the behavior of the temperature of these particular fluids. So for the hot fluid, which we labeled as T sub H, so this is its inlet temperature and this is its outlet temperature, we expect that its temperature is going to decrease because it's being cooled down by the cold fluid. So this is the inlet temperature of the cold fluid, and expected its temperature is going to increase. So this is the temperature diagram for this particular flow orientation. Your delta T1 and delta T2 are these two temperature differences. So this is your delta T2 and this is your delta T1. Now, if it's counter current, we change the position of the delta T's in here. So in here on the left side, you have delta T1, and in here on the right side, you have delta T2. So since it's counter current, so the hot fluid is entering this side, but the cold fluid is entering this side. So they are facing each other when they, let's say, transfer or one transfers energy to another and one receives that particular energy. So the hot fluid decreases its temperature and the cold fluid increases its temperature. Now, this is the manner we write the delta T1 and delta T2. So based on this orientation, you just get the delta T2, meaning it's T sub H inlet minus T sub C inlet. Your delta T1 is T sub H outlet and T sub C outlet. Now, reference books differ in the manner they represent variables. I think this is true with any particular subject. So McCabe has a different manner of presenting the variables in a particular equation, same thing with John Couples, and more importantly, the one that you have in your handbook. But your handbook is in terms of how it is, in terms of its where it is closely related to in terms of representation, it is closely related to McCabe. So my manner of presentation here in terms of the variables will differ from the ones that you have in your handbook. So please check your formulas available in the handbook. You can use any particular formula from any particular reference as long as you know what that particular variable or parameter in the formula represents or what it is. It may be represented in a different manner, but as long as you know what it represents, that you won't go wrong. Okay, as long as don't use a formula that you know what a particular variable or parameter is representing. Okay, so now that you know the delta T1 and the delta T2 that you will place in here in the delta T log mean, the next thing that you are to do is that, or determine, is the temperature correction factor. You have this same diagrams, equivalent diagrams in your handbook. What I have in here as examples are for the 1, 2, and the 1, 4 exchangers, and in here you have the 2, 4. Before you can determine the temperature correction factor, or the F sub T, you need to solve separately the Y and the Z that you need to use for these diagrams in here. The other one also uses the Y and the Z. And what do you have in here are the inlet temperature of the hot fluid, the outlet temperature of the hot fluid, the outlet temperature of the cold fluid, and the inlet temperature of the cold fluid. So just as substitute values in here, and once you have the Y, so you use that for the horizontal axis here, and for the Z, that would be for the curves. If you don't have the exact Z curve for the Z value that you got, then just approximate based on the shape of the curves that are written in here. And then you get already the F sub T, or that's the temperature correction factor. Once you have it, then you go back to the formula that we have in here, multiply it with the delta T log mean, you already have the mean temperature difference. And that's the one that you're going to multiply to the available information. So the available information can either be a pair of the overall heat transfer coefficient and the area for the inside of the tube and for the outside of the tube. Okay, so that's it. If we're going to use this formula for determining the amount of heat that is transferred. What is very important though for you to really remember, that this particular method of determining the Q will only work if all 4 temperatures are known. Okay, all 4 temperatures. I'm referring to the temperature of the hot fluid, inlet and outlet. The same thing with the temperatures of the cold fluid, inlet and outlet. If there's just one temperature that is unknown and you cannot determine it using a simple Q of the amount of heat projected by the hot fluid equated to the amount of heat absorbed by the cold fluid, so you can do that if there is just one temperature that is unknown, and then you already complete the 4 temperatures. So I hope I make sense. So if you only have one temperature that is unknown, just equate the amount of heat that is transferred by one medium to another. Then you will be able to determine that 4th temperature. But once you already have 2 temperatures unknown, then you cannot determine it already using the equating of the Qs, because you already have 2 temperatures. And this particular method will not anymore be applicable. That's the time that we go to the next, which will be using the heat exchanger effectiveness, or it's the epsilon. We represent it as the epsilon. So that's how you decide which of these methods will you use when you design your heat exchanger. Okay? So LMTD will work if you have all 4 temperatures, or if it's possible for you to determine all 4 temperatures, even if initially the problem only gave you 3. Okay? Now we go to the alternative, which is the heat exchanger effectiveness. Okay, you use this when temperatures are not complete. Oftentimes, the outer temperatures are not the one known, or it's not given in the problem. But let's define what is this heat exchanger effectiveness is. So this is the ratio of the actual rate of heat transfer in a given heat exchanger to the maximum possible amount of heat transfer if an infinite heat transfer area were available. So actual amount of heat transferred divided by the maximum amount of heat transfer if there is no limitation as to design in terms of the area, the available area for heat to transfer through. So that is your effectiveness as defined. But we get this effectiveness actually using also a formula. We can solve for it, or we can use the NTU method. So let's go to this two one by one. So in here, in heat exchanger effectiveness, we determine the C sub H and C sub C, all in capital letters, the subscripts. So your C sub H is the product of the MCP of the hot fluid, and your C sub C is the product of the MCP of the cold fluid. I think it's also written, I think, in the next slide. You have here this one, the orientation that is shown in here is counter current flow. And by the way, I think it was emphasized also last year in our class that based on the two modes of contacting the fluids, indirect contact, that is, it's the counter current flow that is more, shall I say, it capitalizes more or uses more the energy of the heating medium. Okay, in terms of design, it's better than co-current flow or parallel flow. So that is why in here in the orientation you have counter current flow. Now let's go to our equation. So this is the equation I mentioned a while ago that you can use if one of the temperatures of the four are unknown. So you equate the amount of heat transferred by the hot fluid to the amount of heat transferred by the cold fluid. That way you can determine the temperature. It's the same equation that you have in here because it's fundamental in heat transfer. That what is rejected by one is absorbed by another in terms of the amount of energy. Now what you have to take note in here, class, though, is that in here you have interchanged the manner of subtracting the temperatures. Since the inlet temperature of the hot fluid is higher than its outlet temperature, it's okay. So the value of this Q is positive. Now, if you miss to interchange these two in here and you miss to write the negative sign before that, then your answer will be wrong in determining the fourth temperature. Because we know that for the cold fluid, we will have, in this case, TCI, your inlet temperature minus the outlet temperature, it would be negative. So that is why if you don't interchange these two, you should have negative written here before the formula. If not, then this is how it should be written. That way, you're just equating values. You don't account for the signs. Missing the negative sign will make you, of course, get the wrong fourth temperature. Now, this is your standard formula for determining the Q. And in terms of heat exchanger effectiveness, this would be it. So this E, or the epsilon that you see here, is the effectiveness, and you have here the C minimum, or its equivalent to the C sub C, the MCP product of the cold fluid. And take note what you are subtracting in here. It's the inlet temperature of the hot fluid and the inlet temperature of the cold fluid for counter current flow. So we're talking about counter current flow. Okay. Now, what about if it's still counter current flow in here? This is the formula that we have, that I was mentioning a while ago for the effectiveness. So in the formula, you need the C min and the C max. So again, the product of MCP of the cold and the hot fluid respectively. And you need the overall heat transfer coefficient and the heat transfer area. It's in here. It's written here. This ratio of the UA product to C minimum is actually the number of transfer units, or the NTU, which we can also get from a diagram. Okay, the value of that can be taken from the diagram. Now, this is for counter current flow formula for effectiveness. For co-current flow for effectiveness, this is your formula. Okay, so a different formula for each of those two scenarios. The diagram that I was mentioning, where you can get the number of transfer units, or you can use the number of transfer units, is these two diagrams. Also, it has an equivalent in your handbook. Okay, now it's either the effectiveness that you will be taking here or reading from these tables, or it is the It is the ratio of the UA to Cmin, and that's the number of transfer units, depending on what the problem requires of you. Oftentimes, this is really meant to be used in determining the effectiveness. So you need here the NTU, so meaning you need to determine this one first, and then the ratio of the C minimum to C maximum. You have these curves here for the ratio. Again, approximate if the value that you computed does not fall on any of the curves that you have here. So A is for counter current flow and B is for parallel flow or co-current flow. That's in the case of the use of effectiveness. And when do we use it? When we lack two temperatures, or the four temperatures that we need in LMTD cannot be completed. Okay. Now in heat exchanger design, we have to consider also what we call as the heat exchanger fouling. Now these are caused by material deposits on the hot surfaces, also due to the presence of impurities in the feed material itself, or in the formation of rust, especially if there are high velocities. If your feed has high velocity, so the formation of rust will be rapid, or if it's corrosive. Now, also if your fluids have high temperature, so heat exchanger fouling can occur. Now, this fouling or these scales that deposit on the hot surface can be an additional or offers additional resistance to heat transfer. And as such, it has to be accounted for. That way, we know really how much of the heat that is being supplied is just made use in the process of, let's say, heating, or in the case of cooling, how much of the heat that is being rejected, because you have the presence already of these scales or deposit. Now you have here a cross-section of a clean tube, and in the side you have the fouled up section of your tube. Now how do we account for heat exchanger fouling? Now I'd like to go back to the original formula that was shown to you, the one in which we did in here, in which you are to use the resistance, because you're not given the overall heat transfer coefficients, but you're given outer and inside areas and heat transfer coefficients. So how are you going to, shall I say, add up the presence of the fouling factors in here? Because this one does not account for the presence of the fouling factors or substances. So if this is your original summation of resistances, by the way, this is the fouling due to the, shall I say, the inner liquid or fluid. This is for the outer fluid, and this is for the wall itself that separates the two fluids. So there's no account as to the fouling material present in our heat exchanger, or in the tube of our heat exchanger specifically. So how do we account for the fouling factor? So you just modify the formula for the R, okay? Or we modify the formula that we have for the U, okay? Never mind the subscript ORO here. This simply means uh, the the outer circle, the inner circle, and the radius in between. So that's what it's meant here by ORO. So in here, you don't have, you don't still consider the resistance due to fouling. If you add the fouling, you have already the U sub I written in this form. So you have 1 over R sub I, and you have 1 over H sub I, R sub I, and this one accounts for the fouling coefficient, okay, the heat transfer coefficient due to fouling in the inner part of the tube. This should be given. So in my scanning, I did scan what is available in terms of the sample problems that you can make use in our textbooks. We are using 2. We have John Couples and McCabe. I can't find one in John Couples, but there's but one example in McCabe regarding this one, wherein you're given an example of the fluid on the inside part, and its corresponding heat transfer coefficient. Okay, so that would be accounted for in here, multiplied to R sub I. And this one is for the wall. That is why you have already the thermal conductivity constant in here. And this is for the outer fluid, the H sub DO. Now, specifically, that problem is example 11.1 in McCabe because there's none in John Copley's. And you're given in the form of a table the value of the inside fouling factor. This is the inside fouling factor or the heat transfer coefficient due to the fouling fluid, the inner part of the tube, and this is the outside fouling factor. Okay, we just add up these two to the standard U sub I that we have without the presence of the fouling material. So read the sample problem that you have here in McCabe as to the use of this particular formula, wherein it accounts already for the presence of the fouling substances. Okay. Now in here, you will have, I have placed in here sample problems for heat exchangers, so read as well those problems. Okay, so we proceed to industrial crystallization. So in industrial crystallization, we determine the amount of water oftentimes that is evaporated. We determine the yield of the crystals and the purity of the crystals. It's associated with the yield. But in terms of the elementary computations associated with industrial crystallization, you can be asked a simple question of determining the degree of supersaturation. So in here, in determining the degree of supersaturation, you simply get the difference of the solution concentration and the equilibrium saturation value of the concentration. So both of these are concentration values. Now for supersaturation ratio, you have it in here. So S as for the supersaturation ratio, and it's equal to C divided by C asterisk. Anyway, they are defined in here already. The reason why I'm giving this to you, because this can be found in Coulson, and oftentimes, as based on the sharing of those who have taken the board exam, probably majority of the problems are taken in books that are not given in school, like McCabe and John Copley's. It's because the examiners then does not have, let's say, shall I say, the stratified way of getting problems for each specific topic. So kung ano lang ang naobra nila nga problem, and ang problem nga may solution, ara na daan kay Coulson, so tihapos kay may solution na daan kay Coulson. Oftentimes, if they take problems, this is just based on the sharing of those who have taken the board exam. Oftentimes, if they get a problem from a particular book, it's the sample problem itself. Damo again, and we have filed it actually before. Just sad to say that the filed problems that were shared to us, I think was in the CPU, in the DC's office, which I think my computer backed down and I cannot anymore retrieve the saved information there. It was based on the feedback of those that have taken the board exam then. Kalabanan, yung ginahatag nga problem is sample problems mo sa libro. Pag kung hindi sa libro, kay Coulson, get. I'd like to, one of our, I don't want to mention his name, one of our top-notcher who graduated as a Laude himself then, he did not have a formal review. He just reviewed on his own because as financially challenged, the family is really financially challenged. He reviewed his own, so his classmates just shared to him the review material, and that's his feedback. Kalabanan, gid kay ginatun-an niya gid ang mga libro nga wala ginagamit nga reference sa school. So kalabanan gid ara sa mga kay Coulson sa mga libro nga wala nahatag sa school, kag sample problem mismo. So that is why I'm taking also problems from those books in which you may find nga ang formula hindi pareho sa gin-represent ni John Copley's kag McCabe. So if you have, I really suggest, and I've been suggesting this ever since I think you have been my students, that you should have textbooks. That's the only way that you can have great retention of the things that are available in that particular book, because you have something to read. You have the physical book that you can read, and you have the sample problems with you to read. Anytime you can go back to and read. If you think, what is it, what is this particular formula, I forgot, then you can go back right away to the book. It's different when you have everything in soft copies. It would be really extremely, I think, challenging and difficult in your case. If you don't have if you don't have your physical book, then have a summary of notes where you can go back to and you yourselves understand. If you have McCabe, if you have John Couples, read, read. If you say it's too much to ask Miss Ali, read all the sample problems if you have the time. And if you have the inspiration, enough inspiration for you to read, but read, not just for these two, but for your other subjects as well. Read the sample problems. Oftentimes, the sample problems in the books are fundamental in nature. They tell you how to use a particular formula. Oftentimes, they're just substitution. But you need the basics more than the very difficult ones, because in terms of application, it's really a skill already. You develop that as you go along. So that's just my advertisement. I remember saying that because this one is from Paulson. You can find this in her reference books, the reference books that we are using. Now, the relative supersaturation ratio uses the supersaturation delta C here and the S. So you have here either S minus 1 as the formula, or you have the delta C over the C asterisk, which is the equilibrium saturation concentration. Now, how do we express the solution concentration? So solution concentrations may be expressed either in terms of the mass of the anhydrate, the material without the water, and the mass of the solvent, or as mass of hydrate, the material with the water, and the mass of the free solvent. Now, as to the what particular thing we use as the set of units or the units for our concentration, that will be dictated by the problem as it is asking for the S and the relative supersaturation. Okay, oftentimes the problem itself will specify the set of units that it wants for these two. So you would know what particular units will you be using for your concentration based on the required unit of these two. Okay. Now I gave you a sample problem on this, I think last year, wherein the unit, the problem specified the units that your S or your relative supersaturation value should be expressed to. Now, we go to the representation of our vacuum crystallizer. So you have the feed, and associated with the feed, we have its solid content represented as X sub F, its enthalpy, and its temperature. We have the vapor, it has also its enthalpy. We have the magma. Now, this is the representation for the magma, and from the magma, we have the mother liquor and the crystals. We are interested with the C, the final product of the crystallization process, which are the crystals. And of course, we're also interested with the amount of water vaporized. Now, speaking of the product, the crystal, so that has something to do with the yield. So the yield of crystals produced by a given degree of cooling may be estimated from the concentration of the initial solution, or the feed that is, and the solubility at the final temperature, allowing for any evaporation if there is, and if there's none, then there's no evaporation, and making solvent and solute balances. Now the last phrase here, which tells you that the yield of the crystals can be determined by making solvent and solute balances. This is the method of Giancouples. So if you read Giancouples, the problem there does not have the formulas that I will be sharing to you. Why? Because it's using this solvent and solute balances. Whereas the one that is introduced by Coulson deviates from that usual material balances, using solvent and solute balances, and accounts already for even the I mentioned it in evaporation, even in the elevation in the boiling point temperature. Even it accounts for the latent heat of vaporization of your feed, or rather of your water. So that's it. So in here, in making solute and solvent balances, you can go back to Jacobs and even McCabe. It's using this one. But for other alternative formulas, that's the one that I'm sharing with you, and that's the one that I taught you last year, and it's taken from Colson. Now, the yield based from Colson's equation is this one. The R is defined as the ratio of the molecular mass of the hydrate, okay, over the with the molecular mass of the anhydrous salt. So the one that contains the water and the one that does not contain the water. So that's the R. The E that appears in this formula is the ratio of the mass of the solvent evaporated to the mass of the solvent initially present in the process feed or in the solution. So these two appears in the formula that can only be seen in Colson. Okay, the R and the E. The C sub 1 and the C sub 2 of course refers to the initial and the final concentration. Now, speaking class of final concentration, you know the initial concentration because it will mention the feed and it will tell you the concentration of the feed. What about the final concentration? There are times, class, that the problem does not specifically mention that the final concentration is this. So it doesn't say it or does not use that particular phrase. Then what tells you or what will you use for the C sub 2? Or what alternative phrase can you find in the problem that tells you that this one actually is the final concentration? So that alternative phrase is the one that is placed in here in the definition. It says here, the given degree of cooling by estimating the concentration of the initial concentration solution, and it's in here. The solubility at the final temperature. So if it does not give you the phrase or does not contain the phrase, the final concentration, the C sub 2 is actually taken from this phrase here. The solubility at the final temperature, that is your final concentration. So don't necessarily look for the phrase that it will say that's the final concentration. Just in case you will encounter a problem that does not specify it. Oftentimes it does not. It simply tells you of the solubility. That's your final concentration, and that's the C sub 2 that should appear in here, okay, in the formula. Now, in determining the E, which accounts for the heat of crystallization, so there are problems that will mention about the heat of crystallization, the latent heat of evaporation of the solvent. So I mentioned a while ago, it's water. Oftentimes, it's just water. Then this is the formula that you will use, okay? Because in here, the problem already tells you additional information such as the heat of crystallization. Or it could be also, class, that you will be able to determine this E. Where can you get it? From the fundamental value in here, the mass of the solvent evaporated divided by the mass of the solvent in the initial solution. So it could be that you can determine the E using this fundamental formula, and from that E, the problem may ask you for the heat of crystallization. Now, you won't be able to get that if you're just simply using the usual material balances that is introduced in Jacobs or McCabe. You can only determine it using this particular formula. So that could be one way of tweaking the problem, giving you a way of determining the E and not giving you the heat of crystallization, but rather asking for it. So you can determine it using this particular formula. So the Q, the heat of crystallization, is in here, and the rest are also given anyway, defined in here below. Okay, so that's for this formula available in Colson. Now, as to design of crystallizers, oftentimes per experience, as what I could see in review materials, it is always the mixed suspension, mixed product removal type of crystallizer that is coming out of the board exam. I'm not saying that it would be this same type of crystallizer that will be given to you or in terms of a design problem in which you will be required to solve. But oftentimes, this is the one that is given in review materials, even in review centers. This is the mixed suspension, mixed product removal type of crystallizer. So in here, in terms of the design equations available for this type of crystallizer, you have in this first formula, you have the magma density. Now, the problem again will not ask you what is the magma density. That would be too straightforward. It may ask you for the solid content. So the solid content in this case is the magma density. So this would be the formula that you will use. Everything in the formula is defined in here. So you have the volumetric shape factor for the alpha, the rho is your crystal density, the nucleation rate, and the G sub D as the growth rate, and the drawdown time. The drawdown time, which is simply the residence time. The time it will take for your magma to stay inside the crystallizer for it to develop into a size. It depends on the size, the size objective of the manufacturer. So when he will, shall I say, withdraw the product already from the crystallizer. So those that haven't yet reached that particular size requirement remains inside the crystallizer for it to grow to that particular size that is required. Okay, so residence time, the amount of time in which your material stays within the crystallizer for it to grow. Now, another formula that is related to MSMPR is the number of crystals per unit size per unit volume of the system. Now, in here, you still have the same parameters that is present on the previous formula. Okay, the G sub D, the T sub R are still there. So this is another formula for you to use. Now, you have here sample problems related to crystallization here. And I have, by the way, placed these particular sample problems also separately in Canvas for you to view. Okay, so we go to the last part, which is the drying. We can have a 5-minute break here. We come back at, my time here is 6:33. Please come back by at most 6:40. We will continue with drying. So we're the last topic of HMT, which is drying. So this refers to the removal of relatively small amount of water from the material, and water is usually removed as vapor. That's gas already by air. So our drying medium is air. And this may also refer to the removal of other organic liquids. So we're not only limiting the removal of solvents in the form of water, vapor, but also benzene can be removed through drying from solids. And this drying procedure is usually the last part for a series of operation in manufacturing, because of course we know that if there's excess moisture present in the material, if it's packaged already, your material will tend to cake, or it will degrade or decompose faster if the moisture content is high. And of course, it would be added cost in transportation because it would be heavier if the excess water is not taken away or dried up from the material. So in terms of the moisture content that may be present in the material, it can be in the form of bound moisture or free moisture. So this bound moisture is the water retained so that it exerts vapor pressure less than that of free water at the same temperature. Now, this particular moisture may be retained in small capillaries, adsorbed on surfaces, or as a solution in cell walls of materials. the free moisture is the water which is in excess of the equilibrium moisture content. Now, we have here humidity because in the computation for the design of our dryer, we'll be using the psychrometric chart, and we take the humidity from the psychrometric chart. And this is the mass of water per unit mass of dry air. Now, in terms of partial pressure formula, so humidity is the partial pressure of water vapor divided by the difference of the total pressure and that partial pressure of the water vapor. That's the humidity. We take this or we read this from the psychrometric chart. Now, we have also in here humidity of saturated air, and that's the H sub O. And by the way, other references will represent humidity as Y. Okay, so in here I represented it as H. So saturation humidity or humidity of saturated air. This is the humidity of air when it is saturated with water vapor. In this condition, the air then is in equilibrium with the water that it contains at the given temperature and pressure. Now, percentage humidity is the humidity divided by the saturation humidity. The percentage relative humidity, which is the R, is the partial pressure of water vapor in air divided by the vapor pressure of water at the same temperature. Now, we also have in here humid volume. So what is humid volume? So this is the volume of the unit mass of dry air and its associated vapor. So simply, it is the volume of water and air, dry air, and the water vapor that it contains. So that's humid volume. Now, the formula for humid volume that you see in here, this will give you SI, sets of units. And as you can see, the units of the humid volume tells you that it is just but the reciprocal of the density of your dry air and water vapor mixture. So you have here cubic meter per kilogram, given that this T should be in Kelvin. So this would be the resulting unit or units for your humid volume. Now, for the time of drying, for the constant rate period, you have the formula in here. It's the initial moisture content minus the critical moisture content, W sub C. Initial moisture content is W sub 1 divided by the product of the rate of drying per unit area times the area of the exposed surface. Now, if this rate of drying is not given or specially stated in the problem, we can use the formula M times the difference of the critical moisture content and the equilibrium moisture content. You can replace their R sub C by M times W sub C minus W sub E. As for the falling rate period time, so this is your constant rate period time. As for the falling rate period time, it would be this formula. And this time, you have an added feature here, an added variable, which is the mass of the material. So it's not present in the constant rate period. So the mass of the material is in here, and still you have the moisture content. Equilibrium moisture content, critical moisture content, and for the omega here, for the W, it's just the moisture content at the time, at the end of the drying time. That would be omega. This omega, by the way, or this W is the total moisture content. So the same thing with the moisture content in here that you have here. And by the way, this equilibrium content should be given by the problem. The same thing with the critical moisture content. It should be given by the problem. Oftentimes, the initial moisture content or the initial total moisture content is also given. Now, so if this is the time for the constant rate period, then this is the time for the falling rate period. Your total drying time will constitute the sum of the two. And if we are asked for the free moisture content, that would be the moisture content or the total moisture content at time t minus the equilibrium moisture content here. the W sub E or omega sub E. Now, in terms of how we classify dryers, so dryers can either be continuous or operating in batch. So there are two broad classification of dryers, and further in each of the classification, uh, we can have contact dryers under continuous dryers, convective dryers, or other forms of drying processes. So it's the same thing with the batch dryers. Now, in terms of these three modes of drying, contact drying, convective drying, or other forms of drying, the feed can also categorize each of these modes of drying. So if it's particulate or solid feed, and it will be contact type of dryer, so this will be your choices for the continuous dryers. You can have the plate, the vacuum band, the horizontal, the agitated or the paddle type, and the indirect rotary. So if it's particulate or solid feed but convective type, so if it's layer type, you have this type of dryer, and dispersion type, you have this type. These are specialized type of drying, the freeze drying, the drying using radio frequency and microwave and even solar. The IR here that you see is infrared, and you have your radio frequency for the RF. So in each of these modes of drying, you further divide them based on the feed that it processes. So it could either be particulate or solid feed. It could be solid, slurry, or pumpable feed, or it could be in the form of sheet or film. So then you can choose the appropriate type of dryer. So this particular diagram will aid you in selecting the appropriate dryer for a particular job or duty that it should perform. Now the basis would be the type of feed or the type of contact of the, let's say, the solid and the air, the heating medium or the drying medium. For batch dryer, we do the same. So, however, in here, we only have two classification for feed for batch dryer. So it could either be particulate or solid feed, or we have the liquid, slurry, or pumpable feed. Now, let me continue. So as to the types of dryers, or the category of drying processes first, we'll go to this. So heat is added by direct contact. So that's in the case of the contact drying here. With heated air at atmospheric pressure, and the water vapor form is removed by air. So the water vapor goes with the air that was used as the drying medium. Now, vacuum drying, this is the removal of water, which proceeds more rapidly at low pressure, and heat is added indirectly. So that's the convective type. So indirect type of drying by contact with the metal wall or by radiation. So vacuum drying. We can have freeze drying as one process here under the specialized type of drying. And this is where water is sublimed from a frozen material. So it need not pass through the liquid phase. It goes straight to the gas phase. So that's in the case of freeze drying. Now we go to the types of dryers. So we have the tray or shelf dryers. Now they are used for granular materials and for individual particles or individual solids that need to be dried. The material is placed on a series of trays, which may be heated from below by steam coils, and drying is carried out by the circulation of air over the material. Now, in some of cases, the air is heated and then passed once through the oven, although in the majority of this type of dryer, some recirculation of air takes place, and the air is reheated before it is passed over each shelf. As air is passed over the wet material, both the temperature, its temperature and its humidity changes. Of course, it's a given that the humidity of your air changes because it already takes up the water vapor that is removed from the dried material. Now, in the case of tray dryers, as a continuation, you have racks mounted on track wheels so that they can be pulled out of the chambers, or in the case of the bakeries. Now, useful when the production rate is only small, and can dry almost anything, but this is labor intensive. So you need labor for loading and unloading. Now, drying time by circulation of air is low. As such, the production rate is small, and drying cycles could take up as long as 48 hours per batch, and may be operated under vacuum as well, so reduce pressure, often with indirect heating. Now, for tunnel dryers, this is when they already have this long tunnels, normally used for fine solids. So in tunnel dryers, a series of trays or trolleys is moved slowly through a long tunnel, which or may not be heated, and drying takes place in a current of warm air. Now, these tunnel dryers are used for drying paraffin wax, gelatin, soap, pottery ware, and wherever the throughput class means the production rate is so large. So throughput production rate is so large that individual cabinet dryers, in the case of tray drying, would be involved, or it will involve too much handling. So alternatively, material is placed on a belt or a conveyor passing through the tunnel. Now, an arrangement which is well suited for vacuum operation. Again, reduced pressure. Now, we have the drum dryers. So this consists of one or more, this is or, heated metal rolls on the outside of which a thin layer of liquid is evaporated to dryness. So the dried solid is scraped off the rolls as they slowly revolve. So effective for dilute solutions, concentrated solutions of highly soluble materials, and moderately heavy slurries. So take note of the applications. So this is not suitable for solutions of salts with limited solubility, or for slurries of abrasive solids that settle out and create excessive pressure between the drums. So that's why your drum dryer. Now we go to the spray dryer. So this may combine the function of an evaporator, a crystallizer, a dryer, a size reduction unit, and a classifier, all in one equipment. All of this it can carry out simultaneously. So a slurry or liquid solution is dispersed into a stream of hot gas in the form of a mist of fine droplets. Moisture here is rapidly vaporized in the process, from the droplets leaving residual particles of dry solids, which are then separated from the gas stream. In here, you have very short drying time, which permits drying of highly heat-sensitive materials. So take note of the specialized application and the production of solid or hollow spherical particles. That's in the case of the spray dryer. Now, this yields product that is ready for package from a solution slurry or thin paste. Not highly efficient, though, since much heat is lost in the discharge of the gases. Bulky and very large, and are not always easy to operate. Bulk density of the tri-solids is difficult to keep constant, and the final dry particles are often hollow, and as such, it's for this application. And the product from a spray dryer is quite porous. As such, it is hollow. It has pores. Okay, we go to the rotary dryers. This consists of the revolving cylindrical shell, horizontal or slightly inclined towards the outlet. The wet feed enters one end of the cylinder. The dry material discharges from the other. Now, heated by direct contact of gas with the solids. And this is desirable for materials that tend to dust. So this is the one that is used in cement manufacturing. So used for salt, sugar, and all kinds of granular and crystalline materials that must be kept clean and may not be directly exposed to very hot flue gases in the case of rotary dryers. Now, for the continuous drying of materials on a large scale, let's say for example, you need to process 1 ton per hour or greater, a rotary dryer, which consists of a relatively long cylindrical shell mounted on rollers and driven at a low speed of up to point Hurst, is suitable. So the shell is supported at a small angle to the horizontal so that the material fed in at the higher end will travel through the dryer under gravity. and the hot gases or air used as the drying medium are fed in either at the upper end of the dryer to give co-current flow or at the discharge end of the machine to give counter-current flow. Now, methods of heating for rotary dryers. So we have the direct heating, where the hot gases or air pass through the material in the dryer, and the indirect heating, where the material is in an inner shell, now heated externally by hot gases. Now, alternatively, steam may be used and can be fed to a series of tubes inside the shell of the dryer, of this particular type of dryer. Now, in terms of design equations that we can use for the rotary dryer, so we have here the heat transfer rate. So the heat transfer rate for a rotary dryer is given by the product of UAV delta T. U is the overall heat transfer coefficient. V, the volume of the dryer. The A, small letter A, is the area of contact between the particles to be dried and the gas. This is now, take note, per unit volume of the dryer. So this is having a unit, let's say, of area over volume. And delta T is the mean temperature difference between the gas and the material. Now, that's for the amount of heat that is transferred, or the heat transfer rate. Now, as for the length of the dryer, the rotary dryer, this is the formula made available in Colson. And you need the Q in here. That is why you're given the formula in here in determining the rate of heat transfer. And you have the other parameters in the formula defined here. So you have the G prime, or the air mass velocity, and you have the delta T L sub M, the lube mean temperature difference between the material and that of the air. Now, we have also for these adiabatic dryers the number of transfer units. Now, if you're wondering why, what is this T sub A1 and T sub A2, the A here represents air, temperature of air, inlet air and outlet air for 1 and 2 respectively. Now, McCabe uses a different representation. Same thing with John Cook, please. So please check what is the representation of those two books. Just make sure that you know the representation that is being used in your handbook, because that's the one that you will be using. But nonetheless, in here, A here is the air temperature, 1 and 2, inlet and outlet temperature. The T sub W is the wet bulb temperature of the solids. Okay? Wet bulb temperature of the solids, the water that your solids contains. That is why it's T sub W. Now, we also have through circulation drying in packed beds. This topic can only be read from Jen Please. I haven't read this in McCabe. This is not available in McCabe. So I place it in here because it's also important. Now, this is drying, wherein the drying gas passes upward or downward through a bed of wet granular solids. So in this case, class, the air that is being used for drying not only passes parallel to the surface of the material that is to be dried, but it passes through the top portion and the bottom portion of the material. So the drying gas passes upward or downward through a bed of wet granular solid. So it depends. It could be either only passing upwards or downwards or both. Now, often the granular solids here are arranged on a screen so that the gas passes through the screen. So it's either from the bottom going up or from the top going down, so that the gases passes through the screen and through the open spaces or voids between the solid particles in your screen or in your bed. So because we're talking about here through circulation drying in packed beds. Okay. Now this is the amount of water removed by the gas in this particular type of drying through circulation drying. So R with the unit of kilogram water per hour per square meter of cross section. available, of course, for your drying medium air to pass through. So that is why it has per unit area here of cross-section. If you know the cross-sectional area, if there's a way for this to be determined, then you have the amount of water removed from the bed in mass per unit time, unit. Now, the G is the kilogram of dry gas. If it's air, oftentimes it's air that is supplied per hour. Again, per unit per square meter or per unit area of the cross-section where it is going to pass through. Now, what about the thickness of the bed? So in here, you are able to determine how much of the water is removed in the bed. What about in terms of the thickness of the bed, which is the Z? So in here, you need a lot of parameters to consider. So you need the C sub S, the humid heat of air, water vapor mixture. This is comparable to the CP of the dry air and the water vapor that it contains. Again, so it's just taking the CP of the dry air and the water vapor that it contains. It's the humid heat. We have actually covered this last year, the humid heat thing. So please review on that. Then H is the heat transfer coefficient. The small a is the surface area of the solids. Again, per cubic meter volume, bed volume, that is. Wet bulb temperature, again, for the T sub W, T sub 1, and T sub 2 for the inlet and outlet gas temperature or air temperature. So notice in here, in John Couples, it does not have already, it does not anymore place A in the subscript of the T's. So it's simply 1 and 2 understood to be referring to the temperature of the drying medium. Now, that's for the Z. How thick should the bed be? Okay, or how thick should be the solid that you will that is placed on the screen, where your drying medium is to pass parallel through or through it, like coming from the bottom going up or from the bottom going down, depending on the design. Now, as for the drying time, still on the topic of through circulation drying, so you have this constant rate period drying time and falling rate period drying time. All the parameters that you see here are well defined in John Couples because this was taken in John Couples. Go back to your John Couples and check on these formulas. And again, you have here the humid heat, you have here the wet bulb temperature, you have the lambda sub W. The X sub C here is the critical moisture content. The X sub 1 is the initial moisture content. So it has a different representation already because we're talking of a different reference material. So what is important is you know what that does this represent. Now this formula for the constant rate period drying time and the falling rate period drying time is applicable for particles of diameter ranging from 3 to 19 mm and shallow beds about 10 to 65 mm thick. Now, if the range of the diameters and the bed is thickness is out of range, then this particular formula will not be in use anymore. And you will be able to read also that this particular formula is empirical in nature. Now, if we look closely in the formula class, I'm not so sure if this was covered last year in our subject, but I have covered this during face-to-face time. This is very cumbersome because you get to see here an H, you get to see an H and an A. Before you can even determine the drying time here for the constant rate period and the falling rate period, you have to determine first the H and the A and then plug it in the formula. And what would be the formula for the H and the A? So this is for your H, and you will use a different formula for the H depending on what set of units is your problem working on and depending on this. So this H formula here is applicable if the particle diameter, the G sub T, and the mu, the viscosity is greater than 350. If it's less than that, you use the formula below for the H. Okay? And then for the A that I have mentioned, for spherical particles, this will be your A. For cylindrical particles, this would be your A. And for cylindrical particles whose diameter is not given, this will be the formula that you will use. So there's a need for you to first determine this based on the given information before you can go to this one, determine the drying time. Some of the parameters here I can determine, I can remember. This one is the void fraction. And the rest you need to look up. This one is the heat transfer coefficient, of course. This one is the diameter of the cylindrical particles. The rest that I haven't mentioned, please look up in Genpo please as to what they represent. Okay, there's a sample problem there in the Genpo please as to the use of this particular set of formulas applied to through circulation drying in packed beds. Now, as what I can recall, I was not able to cover this to you last year because we lacked the time already. Okay, so that's it. Now, for drying, you also have your solved problems in here, which you can browse separately on the document that I have shared with you in Canvas. Now, I'm sure you have a lot in your hands, but if you have the time, and stop sharing. If you have the time, look through the sample problems that I have shared